Today we begin the matrix toolbox. What matrices are, how we name their entries, and how we do basic operations. The big idea is that matrices are not just tables of numbers, they are machines we can compute with. Think of a matrix like a well-organized spreadsheet that actually does math for you. The size m by n means m rows and n columns. A 1 by n matrix is a row vector, and an n by 1 matrix is a column vector. If you mix up rows and columns, the matrix will feel personally offended, like mistaking a person's last name for their first name. In Aij, the I subscript tells you the row, and the J subscript tells you the column. A good habit is to say it out loud, row first, column second. It's like coordinates on a map. If you swap them, you end up in the wrong city. Square matrices show up constantly in linear algebra because many special operations need them. The diagonal is a big deal because it's where several important properties live. Think of the diagonal as the matrix's spine. A lot of structure hangs off it. Same size is non-negotiable. You can't add a 2 by 3 to a 3 by 2. Entry by entry means each position is handled separately, like matching seats in two stadium sections. Trying to add different sizes is like adding apples to parking spaces. A scalar multiple is just scale the whole matrix. Linear combinations are built from add, subtract, and scale, so the sizes must match. Think of it like remixing the same song. You can amplify and blend, but you can't remix two songs with different track lengths. Matrix multiplication only works when the inner dimensions match. Columns of A must equal rows of B. Then the result uses the outer dimensions, rows of A by columns of B. It's like a handshake. The hands must match, otherwise the handshake becomes an awkward situation like when you don't know whether you are shaking hands or fist bumping an acquaintance in the gym. The first entry of AB comes from row 1 of A dotted with column 1 of B. You repeat that idea for every column, then for every row. It's repetitive by design, like doing reps at the gym, except the weights are numbers and the soreness is mental. AX equals B is the one-line version of the whole system. That single equation secretly contains all the equations at once. It's like compressing a folder. Same content, less clutter, fewer chances to lose a minus sign. This interpretation matters a lot later. Solving AX equals B is the same as asking if B can be made from the columns of A. So the unknowns are not just numbers, they are weights in a recipe. Think of the columns as ingredients and X as how many scoops you use. Transpose is a flip. Rows become columns. Doing it twice brings you back to the original matrix. It's like turning a shirt inside out and then inside out again. Eventually, it stops being dramatic. Trace is add the diagonal, but only for square matrices. Later, trace connects to deeper ideas, but for now it is a clean, simple computation. It's like checking the spine of the matrix again. You read off the diagonal and add. Here are two equally useful ways to think about AB. Column view. AB is built by multiplying matrix A by each column of B. Row view. AB is built by taking each row of A and multiplying it by B. The partition note is just a dimension check. The pieces must fit so each smaller product makes sense. In other words, matrices are old-fashioned dealers. A deal is not final until a handshake is done. This is a powerful viewpoint. Multiplying by A transforms each column of B1 at a time. So AB is A applied to every column of B. It's like A is a machine and each column vector is a separate item going through the conveyor belt. Correct answer is D. Inner dimensions match 3 and 3. So AB is defined, and the result uses the outer dimensions, 2 by 4. Correct answer is C. Addition needs the same size, and 2 by 3 is not the same as 3 by 2. Multiplication AB and BA are both defined here, but they give different sizes, which is very on-brand for matrices. Correct answer is D, because the diagonal is 4 and 1, and 4 plus 1 equals 5. Trace is always add the diagonal. It's like the matrix's two most important seat numbers in a tiny theater. Add them and you're done. Today you learned the core matrix moves: size, entries, addition, scalar multiples, multiplication, transpose, and trace. The most important habit is to check sizes first, especially for multiplication and addition. If you check dimensions early, you avoid 90% of the pain later. It's like reading the label before you microwave something. Small effort, huge reward.